Section 3.3 Polyphase Synchronous Generators. Section 3.31 A Simple Generator. Electric generators are all based on the fundamental concept of electromagnetic induction developed by Michael Faraday. The electric power industry is based on some energy source forcing a fluid, such as steam, combustion gases, water or air, to pass through turbine blades, causing a shaft to spin. The function of the generator is to convert the rotational energy of the turbine shaft into electricity. A simple generator. This slide shows that Faraday discovered that moving a conductor through a magnetic field introduces an electromagnetic force across the wire. The electromagnetic force is also called a voltage. So, for example, this figure shows this is a magnetic field, the N poles and the south pole, and when a conductor moves during this magnetic field, it will cause a voltage will be created. A generator is designed to cause a relative motion between a magnetic field and the conductor in which the EMF is to be introduced. These conductors are called armature. Most large generators have armature windings fixed in the stationary portion of the machine. So this is called stator. And the relative motion is caused by rotating the magnetic field. This is called the rotor. Let's consider a simple generator shown in figure 3.10. Where this one has there's a rotating, there's a magnetic, and there is an iron like the shape backward C, and on this iron winding is attached with around the stators. So when this magnetic field rotates, it can generate the change of flux and will cause the voltage being generated. So the rotor is just a two-pole magnetic with one north pole and one south pole. The stator considered as an iron and some copper wires wrapped around the iron. The iron in stator is to provide a low reluctance path. So that we can have as much as flux possible to flow across the copper armature windings. As we know, the changing flux in stator will create electromagnetic field, the electromotive force, and also called voltage across the windings. So as the rotor turns, magnetic flux passes through the stator and the armature windings. If this flux would vary sinusoidally, and according to Faraday's law, when a winding links a time-varying amount of magnetic flux, there will be a voltage being generated across the winding. The E is equal to N multiplied d phi dt. Now the question is, if we want to generate a voltage at a frequency of 60 Hz, how fast the rotor should rotate? The shaft rotation rate is equal to 1 revolution per cycle multiplied 6 cycles per second and multiplied 6 seconds per minute. That is equal to 3600 revolution per minute. So to generate 60 Hz using a 2-pole generator, require that the iron turns a fixed rate of 3600 RPM. And this fixed speed machine is called a synchronous generator because it is synchronized with the utility grid. In the system utility grid, the voltage and current is also a sinusoidal waveform with a 60 Hz. The magnetic field is created by sending a direct current through brushes and slip rings into conductors. So this will create the magnetic field. So we won't have using a permanent magnet, but rather than that, we use the DC through brushes and slipping rings to create the magnetic field. Solent pole rotors are less expensive to fabricate and are often used in slower spring hydroelectric generators. The high-speed turbines and generators use round rotors because round rotors are better able to handle the centrifugal forces and the resulting stresses. Field windings may be embedded into slots that run along the rotors. And the silent rotors shown in this figure 3.12b. This is a round rotor, and this is a silent rotor. The left side figure shows a 2-pole machine with a round rotor, and the right figure shows a 4-pole generator with a silent rotor. The 4-pole generator have 4 poles in both the rotor and the stator. When we add more poles on the generator, we'll allow the generator to spin slowly. The rotor speed is a function of number of poles, P, and output frequency, F. So the shaft rotor rate is equal to 1 revolution divided by 2P divided by 2 per cycle, and multiply frequency cycles per second, multiply 6 seconds per minute. Therefore, the rotor's speed, the shaft rotation rate, is equal to 120 frequency f divided by number of poles p. So the table 3.2 provides a summary of rotor speed required for a single generator to deliver power at 50 Hz or at 60 Hz. So if we have a two-pole generator, the rotating speed to generate a 50 Hz frequency is 3,000 revolution per minute. If to generate 60 Hz, we require the rotor speed at 3,600. For a four-pole generator, to generate 50 Hz, it requires 1,500 RPM, and to generate 60 Hz, it requires 1,800 RPM. Now finish the section 3.3.